Welcome to HamCram2018. You are about to embark on a groundbreaking journey into the world of amateur radio. This class is designed to acquire your technical class license. So sit back, enjoy the ride. Sponsored by PittsField Community TV.
Okay, welcome back to HamCram 2018. I'm Kilo Alpha 2 Papa Tango Echo, Steve. And if you can remember my call sign after the meeting, I'll give you a free cup of coffee. How's that? Okay, we're going to continue on with Technician License Class, I guess, is the title of this segment. Picture this, okay. Okay, picture this. As a new technician class operator, you should be familiar with the identification of simple schematic diagram illustrations. This is the fun one. In the next few questions, we'll take a look at some schematic diagrams with symbols that you should know. We will home in on identifying individual symbols in the schematic diagrams for your exam. Don't panic, it's easy. Yeah, that's what they said last time. Now let's check ourselves. The symbols on an electrical circuit diagram schematic represent electrical components. So I guess they're just basically saying schematic symbols represent electrical components. So far, so good. Schematic diagrams allow us to see exactly how components are interconnected right down to each and every lead. So yeah, in red they're saying basically you're going to be able to see how everything is connected with a schematic diagram if you have one on hand. Oh, good. Another figure. Component number 3 doesn't have a squiggly line like a resistor, but rather a coil type line. So it is a variable inductor because it's variable because we see tap points on the hump lines and a line with an arrow indicating the inductor can be adjusted to any one of the taps. So yeah, they're saying here figure 3 is called a variable inductor, and basically whenever you see a line through it, like you can see those other items, number 2's got a line through it, that's also what they call a variable capacitor. I don't know if I'm spoiling it for the next question, but in general practice, whenever you see that line drawn through anything, it means it's variable. But here they're saying number 3 is a variable inductor. Okay, component number 4 looks like an antenna. That antenna is tuned by some of the preceding circuit components. So yeah, number 4, that's a very common symbol for an antenna, basically a triangle with a line through it. And I know they always try to put the antenna off to the side or up in the schematic diagrams. They kind of have them like a real antenna would be for a radio. They have them kind of thrown out off to the side a little bit, out away from everything else. So that is an antenna number 4. We use series and parallel coils and capacitors to develop a tuned circuit inside your new radio. Another name for a coil is an inductor, and when used with a capacitor, you now have a tuned circuit. Okay. And this is showing off a bunch. There's quite a lot here. A lot of different schematic symbols here. They're giving you, looks like about maybe 20 or so. But the basic ones there are more or less on the left upper corner. You got your resistors. Resistors are always going to have that squiggly kind of sharp line on them. And then they show capacitors, usually have the separation there. One thing they're not saying, which is a little bit of a side note, is that fixed capacitor, the bent side that's half circular would be the negative and the positive would be the other side. But you basically have some, below that you've got some wiring just showing wires crossing that they have the dot in front of them, tying them in. That means they're connected. And then you've got your inductors, which they mentioned before, variable and fixed. Then you've got your diodes. There's no such thing as really a variable diode, but there they're showing a LED with the arrows, which means it's emitting light out. And you've got your basic diode rectifier, Shakti diode, transformers. There's a bunch of different transistors. I think they throw I haven't seen any FET questions yet, but it might be probably not on the tech exam, but maybe in a future exam you might see some of those more fancier semiconductors. And you've got batteries, grounds, IC amps, logic. There's quite a lot here. Relays, the antennas, and a crystal and a speaker. A resonant circuit must contain at least one inductor and one capacitor. It also may have other components. The resonant frequency of the tuned circuit is the frequency at which the inductive reactance and the capacitance, reactive capacitance, are equal. It is one of the most crucial circuits in all of radio. Resonant circuits of one form or another determine the frequency of operation of all radio devices. So there they're pretty much saying a resonant circuit is the fundamental basic of radio operation, receiving or transmitting, and it consists of an inductor and a capacitor. Okay, this figure will be found on your actual technician class exam sheet, either with the question or on the last page of your examination materials. Component number 1, that squiggly line, is a resistor. Can you imagine current flowing through all the squiggles offering resistance? I guess that's one way to imagine it, but again, the resistor is a very, very distinctive component. It's also a very popular component. You'll see resistors in schematic diagrams all over the place. It's got to be one of the most popular ones in there. Resistors and capacitors are very popular. Okay, component number 2 is our friendly transistor, as opposed to, I guess, a hostile transistor. The arrow is not pointing in, so it is an NPN transistor. So there you go. Number 2, right in the center, is a NPN transistor. It's a very, very common style transistor. The NPN is used in, a lot of the older gear from the transistor era up to, I guess today they're still using them as well. So you'll see that in schematic diagrams quite a bit. Okay, and it says it's an NPN transistor. This one controls the flow of current much like a valve. So yeah, they're kind of giving you a basic operation of the transistor, turning it on with the resistors. They're actually helping the transistor get turned on. To turn on, number 3 is a lamp, by the way, and number 4 is a battery. So it's just an easy way of turning on a light with a transistor, using it as a switch. Okay, component number 3 looks just like what it is, a small indicator lamp. Looks like a lamp, doesn't it? So I guess it's up to you to figure out if it looks like a lamp or not, but we're pretty close. So they're saying number 3 there is a lamp. And one other thing is you usually see lamps, in this case it's tied right to the transistor near the battery, and they usually do try to put the light right near the battery source, or the end of a switch. In that case, is a transistor switch. It takes voltage to make this circuit work, and we get the voltage from the battery. Component number 4 is the battery. And I don't know if they mentioned it, but that pitchfork-looking thing pointing down is a ground. So here they have the emitter of the transistor grounded, and then they have that short side of the battery, which is number 4, grounded, and then they also have the input to the whole thing, which is 5, grounded as well. And they might say that on the next one here. Your handheld may have one of these, a single pole, single throw switch. It's single in both senses because you see only one wire going to the switch and only one single contact point. Single pole, single throw. So right there, that is, let's see, that'll be number 3, is a switch there. Just 2 circles with a little angle drawn in between it, indicating it's off right now because there's a gap between the center slanted line and the other side of the switch contact. Component number 4 takes in everything around it and is a transformer. Voltage is passed from the windings on the left to the windings on the right, with the 2 vertical lines representing an iron core. This transformer looks to have about the same number of turns on the primary and secondary, so the amount of voltage going in will be about the same as the amount of voltage coming out the other side. So that's a transformer, what it physically looks like in the real world. And it says, okay, you're doing so well. Let's turn you into a master engineer. No pressure. And look at figure number 2. Component number 6 has 2 parallel, sort of, plates separated by an insulation. So it must be a capacitor. So they're saying here, component number 6 right there. Yep, that's a capacitor. And again, just for a side note, if you're interested, the ground side is always the curved side of the capacitor. That's what they actually call a polarized capacitor, because it's got a negative and positive to it. So that is a capacitor. See the little arrow symbols on component number 8 showing the effects of light. Component number 8 is a light emitting diode, an LED, easy. I guess you've never seen those before. But LEDs are really, really popular now. They're all over the place, and it's hard not to bump into them these days. That one looks like a white LED. Component number 9 is indeed a resistor, but it has a variable tap point on it. So it's a variable resistor. We'll formally call it a potentiometer, and this could be the volume control on your handheld. Your larger high-frequency transceivers may have a mechanical meter movement to illustrate incoming signal strength. Even if it's an LED or LCD readout, we still call it a signal strength meter. So that would be the analog type meter there with the white background and the red needle kind of indicating midway over. That's also called your S meter on your radio for. Here they say incoming signal strength. So I guess the older gear out there sort of still has these analog meters on them. The newer ones have the more fancier graphical displays and LCD and you name it, all kinds of interesting things out there on the newer radios that indicate signal strength. Most of your handhelds don't have one, but a mobile radio that puts out 50 watts will likely contain a relay. The relay is a mechanical switch opened and closed by current passing through a coil, creating an electromagnet. As soon as the coil is energized, the switch goes from one state to another. If you want to run your handheld on house power, you'll need a power supply that will provide regulated 12 volts to your handheld input circuit. The power supply must have a good regulator built in so that it doesn't exceed the 12 volts DC input that your handheld works with. Never transmit from your handheld when plugged into an AC wall wart, because there is not enough filtering within that wall wart for a good signal. It's okay for listening, but unplug before transmitting. When you purchase your new dual band handheld, it will come with a wall charger that plugs into the side of your radio. The wall charger contains a small transformer that takes 120 volts AC on the primary and steps it down to a lower AC voltage on the secondary. Diodes and capacitors then filter this lowered AC and convert it to 12 volts DC. The common wall wart contains all the circuitry, and newer switcher wall warts are much lighter in weight, and the transformer is extremely small. So basically they're saying that your converter is taking your 120 volts AC on the wall. They call it here a wall wart because I guess it looks like a wart when it's stuck on the wall, kind of a slang term they use now for them. So it takes your AC and it takes it down to 12 volts DC by rectifying it with, in the old days they would rectify it with they would step it down with a transformer, rectify it with diodes, filter it with capacitors. But now what they do is they build everything into what they call switch mode power supplies, which is what they're kind of saying here. When you hear the word wall wart, they're pretty much saying it's going to be a small, tiny switch mode power supply converting AC to DC. If you ever look inside the modern ham radio, you'll see rectangular chips that are large-scale integrated circuits. These chips contain thousands of semiconductors in one nice, neat package, abbreviated ICs. So right there, those are two, I would say those almost look like outdated ICs in these days. Those are, I know what they're called, those are called dual inline package ICs. Those are sort of the traditional type of ICs that came out back in, I say, the 70s and 80s, but now you've got your ICs, you know, look a lot smaller now. Actually, that IC in the top there, you can actually see a little window. It's like a round circle, and that square in the middle, and I don't know, depends on how good your vision is, you can see tiny little leads, like little hair whiskers coming out of that square. That's the actual IC. And now what they do is they take that, and they don't bother surrounding it with that big case anymore. They'll just find ways to save space and put that on the boards. And microelectronics can fit billions of transistors now in small spots like that. Doubling your power will lead to a power increase of 3 dB. Halving your power will lead to a 3 dB decrease. But since we're going from 5 watts to 10 watts, we're doubling our power, and that's a 3 dB difference. So it says it's important to know about decibels because they're used extensively in electronics. The decibel is used to describe a change in power levels. It is a measure of the ratio of power output P1 to power input P2. It's relatively simple to calculate a dB power change. Remember this table. So they're saying 3 dB is a double power change. 6 dB would be quadruple power change. 9 dB is an 8 times power change. 10 dB is a 10x power change, and all the way through up to 40 dB. You can kind of see how it exponentially increases with each dB increase. Now we go from 12 watts down to 3 watts by pushing the low power button on our small mobile radio. This is a 4 times decrease. 4 times 3 equals 12. A 4 times decrease is a power decrease of 6 dB. So this gets a little confusing. Even I'm not an expert at it with the dB. That was one of my weak spots on the tech exam. Hopefully I'll learn it here by teaching it to you guys. Now we add a linear amplifier. Normally I don't recommend any linear amplifiers as you're getting started as a technician class operator. Going from 20 watts to 200 watts is a bit dangerous, and that is 10 times increase in power. 20 times 10 equals 200. 10 times increase equals 10 dB. Another thing on dBs, my Elmer, when I first started, got my exam, my novice test, he said a decibel is 1/10 of a bell. That was how he described it. So sort of a smaller measurement than a bell, you know. But I guess, you know, a bell must be quite significant, you know, quite a lot more than a decibel, 10 times more. Okay, and this one says LED stands for light emitting diode. And this is that red, green, or amber indicator that comes up on your handheld when you're transmitting. The LED draws almost no amount of current and will last for hundreds of thousands of hours without burnout. This is a big improvement over our older radios with grain of wheat light bulbs. LED equals light emitting diode. So I do remember when LEDs first came out when I was in school, and you know, they were basically red and green, not too many yellows at the time. But now you've got white LEDs, and I've learned the white LEDs, they're kind of hard to get. They have to kind of put a blue in there and get the white to have the white to come out. But I've noticed, I don't know if it's true or not, but the white ones don't seem to have a long lifespan. I mean, I've yet to see in all my years a red, a green, or a yellow LED burn out. I've actually never seen it. Some people have said they've seen it, but the chances are very small. But I've seen more white LEDs going bad than any other color lately. Okay, and this says, let's see. Okay, this is an LED again. I guess it's showing your keyboard, and yeah, it's showing you a little bit of a circuit there. You know, like pressing a key activates a pulse network, which then triggers a transistor to switch, and with 5 volts on the anode of the LED, current travels down in the direction of that arrow pointing toward the transistor, goes through the collector, which is the top, and passes through the base a little bit, and then comes out the emitter, which is the arrow pointing to the ground there. And let's see. Okay, and they're also showing you how the LED giving off light, and they're drawing that squiggly blue line over to it, hits what they call a phototransistor, which basically, if you notice, it has no base. Like the other transistor's got a base coming in the input. The input in this case is the LED giving off the light. That actually biases that transistor and puts 5 volts through that transistor, and then here they're sending the output to a decoder circuit. And the diagram below that is saying, I guess that's showing you the kind of how the light bounces around in an LED. Solid, transparent, colored, plastic channels much of the light out of the rounded end. And yeah, I guess there's a little LED chip in there, which is actually doing all the hard work. And you got 2 terminal pins, an anode and a cathode. And below that, they've got what they call 7-segment LEDs. They've been around for quite a while. Basically, you can put up any number, 0 through 9 on there by lighting up different segments of each of those is an LED. Each segment consists of an LED, and then they're showing you, I guess, an LED array, which is, I guess, similar to that, how that 7-segment display is working more or less. Closing the switch lights up a segment. A good visual indicator on a handheld radio is the LED, the light emitting diode that is often used as a transmit indicator. To keep you from running out of pencil lead, we can abbreviate 1,500,000 hertz as either 1,500 kilohertz or 1.5 megahertz. From hertz to kilohertz, move the decimal 3 places to the left. From kilohertz to megahertz, move it 3 more places to the left. So yeah, that's a quick way of abbreviating things. You can also, if you wanted to be fancy, you could also, instead of saying 1,500 kilohertz, you could say 1,500 kilohertz. It's the same thing basically. Whatever's more comfortable for you to do. There are 1,000 megahertz and 1 gigahertz, so we can simply divide by 1,000 to get the final answer, 2.425 gigahertz. Remember kilo. Kilo means 1,000. 1 kilovolt equals 1,000 volts. Watch out for answer A. Okay, I don't know if that's a hint or a warning or. 1 milliampere equals 1/1000th of an ampere. 10 times 10 to the minus 3. Therefore, 1 ampere equals 1,000 milliamperes. Divide milliamperes by 1,000 to convert to amperes, or move the decimal point 3 places to the left. Calculated keystrokes are clear 3,000 divided by 1,000, and the answer is 3. So there's a little bit of a chart there to reference things. So, yeah, calculators pretty much do most of this stuff for you anyway. It's a good idea and fun exercise for some of us anyway to memorize all the metric prefixes. They're used a lot in radio electronics. There are also 1,000 kilohertz. There are also 1,000 kilohertz and 1 megahertz. So 28,400 kilohertz is equal to 28.4 megahertz. Always remember that if the unit is smaller, you need more of them. Your handheld transceiver can also be dialed down to minimum output power, dramatically conserving battery life. 500 milliwatts can be converted to watts by moving the decimal point 3 places to the left. So a handheld at 500 milliwatts output is transmitting 0.5 watts of power, the same as a half watt of power. Believe it or not, you can make many contacts through local repeaters at a half watt of power, and your batteries will love you for it. Your new dual band handheld might offer as much as 5 to 7 watts of output power depending on the battery pack voltage. The transmitter could actually draw as much as 1,500 milliamperes, but don't panic. With all those numbers, move the decimal point 3 places to the left to go from milliamps to amps. In this question, to convert 1.5 amps to 1,500 milliamperes, move the decimal point 3 places to the right, 3 places. A picofarad is 1/millionth, 1 times 10 to the minus 6 of a microfarad, or 1 millionth, 1 times 10 to the minus 6 times 1 times 10 to the minus 6 equals 1 times 10 to the minus 12 of a farad. Move the decimal point 6 places to the left to convert to microfarads, or 12 places to the left to convert to farads. If you do the math, you'll find the answer is 1 microfarad. We measure the receiver capabilities on a handheld in microvolts. The word micro means 1/millionth, mega means million, kilo means 1,000, and milli means thousandth. Micro means 1/1,000,000th. Rosin core solder is commonly available at the same place you purchase your soldering iron or gun. A little soldering pen is fine for working on tiny circuits, but you're going to need a massive soldering iron or a big 200-watt soldering gun if you plan to install coax connectors properly. Always use rosin core solder. Wear protective glasses too. Eutectic solder is a special alloy of lead and tin designed to melt at the lowest possible temperature, and this is recommended if you do any surface mount soldering, an increasingly more valuable skill. It's easy to tell if you made a good solder connection. The solder looks shiny. However, a cold, poorly soldered joint looks grainy and dull. Every amateur should own a multimeter. The multiple function meter can measure voltage, current, and resistance and check continuity. Even an inexpensive multimeter is better than no meter when you're trying to check out a circuit in the field. You can buy an excellent multimeter for less than $25. The only real difference between a $25 meter and a $300 one is not the accuracy, but how many times you can run over it with a Humvee or drop it from the top of a tower and still have it work. Most experienced electronic technicians eventually end up doing the above and more to their meters, so they prefer to get the best meters they can afford. At any time you are checking a circuit with an ohm meter, make sure the circuit is not energized. If you check any circuit with voltage on it, you will probably toast the ohm meter for life. You don't want to do that. You're likely to damage your brand new needle multimeter by measuring voltage if you accidentally leave it in the ohms reading setting. If you have a big old capacitor hanging around in the shack, keep it handy. That big old capacitor has a telltale signature when you check it with an ohm meter. On a high ohms reading scale, the discharge capacitor will first look like an almost short circuit and then show increasing resistance as the capacitor begins to charge up from your ohm meter's test. Thus, if you connect your multimeter set to ohms to the capacitor, it will initially indicate low resistance and then show increasing resistance.